So let's create the building block of a test function. It's not quite going to be a test function yet, but the fundamental building block. There's many functions that could do this, but there's a couple of standard choices based on the mathematics we know already. And so what do we want to create? I want to create something that's not identically the zero function, but that is zero on a large set, not just at a few isolated points. So I want to create something in particular that's zero for all negative values, and then non-zero up here. And it's actually going to be non-zero for all positive values. It'll have to be zero at the origin, just because that's the limit of these zeros. And the crucial thing is to make it smooth at the juncture. And to do that, we really need this non-zero part to vanish to infinite order. It has to have zero value and first derivative and second derivative and second and third derivative and fourth derivative. Another way to say it is it's got to vanish faster than any polynomial. Okay, and that's a real big hint as to a good way to create this thing, because the one thing we are going to use is that the exponential function that grows faster than any polynomial. Now that's as x goes to infinity. Okay, well, we need something that's going to work at 0, so we're going to take e to the 1 over x. Now wait a minute here. We want it to vanish really fast. Well, that's easy. We take 1 over that, or equivalently we take e to the minus 1 over x. So that's going to be that part. It's really not too weird. It's using the most important function ever invented. So strictly speaking, our function f is going to be e to the minus 1 over x for x greater than 0, and just 0, arbitrarily set to 0 elsewhere. And the point is that usually we're used to having, when we look at piecewise functions, I hope your intuition is to be like, well, where's that going to go wrong? Is that discontinuous? Is it differentiable? Where does it go wrong? And the cool thing is, from the point of view of differentiability, it never goes wrong. And that's pretty amazing. So that's what we want to show. So I'm going to work out the details of that. And it's good to stop, either pause and do it yourself, or if you've seen this before, you can cut to the chase. But it's a very cool workout with just doing calculus carefully. Okay, so oh yeah, so the graph, it looks basically like what I gave you, 0, and then it's going to come up, and then e to the minus 1 over x way out here. X is getting really big, 1 over x is getting small. That minus, it's e to the minus a small number. That's going to be asymptotic to 1. One thing is it never gets to 1. And we're actually going to eventually, or pretty soon, we're going to want to create a function that goes 0, positive, 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 and then exactly 1, just like it hits exactly 0 over here. This is not going to quite do that. But that's what the graph looks like. And, oh yeah, and obviously, it's definitely differentiable here. It's definitely differentiable here. The only issue is showing it's nice at x equals 0. Now, to analyze at x equals 0, to take derivatives, we still need to know what's going on right near there. So we're going to need to take a bunch of derivatives of this formula. And that gets slightly messy, but we can do it in a pretty way. So we can avoid most of the messiness. Okay, so b, well, f is continuous at 0. Well, the limit as x goes to 0 minus of f, that's obviously 0. And a nice trick that we're going to use for the rest of this time, remember the idea was the x behaves in a very predictable way, in the right way, when x goes to infinity. We took a 1 over x. We're just going to change the variables back. So this is, because we're going from 0 plus, we use this formula. And then let's just say y equals 1 over x. That's going to be the limit as y goes off to plus infinity of e to the minus y. And that's known to be 0. And of course, we're going to use a lot more about that limit, not just that it goes to 0, but that it goes to 0 super quickly. It's going to be the whole point here. Okay, so we haven't taken any derivatives yet, though, okay, at the point 0. So we're going to look at the left-hand derivative is clearly 0 because it's just coming in from 0. I'm not going to show that. The right-hand derivative, if we can show that that exists, n is also equal to 0, then we'll be good. We've already shown the value is 0, it's continuous. We just need to show this guy. And we really have to break out the definition, because for a piecewise function, you can't just evaluate e to the minus 1 over x at 0. It doesn't evaluate to anything. But we're just going to look at this. So this is e to the minus 1 over h minus, and now it's really crucial to know the value at 0, but we know that. It's set to 0. It's artificially defined to be 0. And then over h. Okay. And now, again, we're going to just do the change of variables. Y equals 1 over h. E to the minus y over 1 over y. Or in other words, y e to the minus y. And that's a fairly standard limit if we want to actually be careful about it. Then we're actually going to put the e to the y on the bottom to let L'Hopital's rule work. So L'Hopital's rule in the form of infinite limits says that if these guys are both going to infinity, then I can take the derivatives, top and bottom. And of course, the beautiful thing is that gets simpler and that doesn't change. And that we just did. That's equal to 0. Okay, so the left-hand derivative is 0, the right-hand derivative is 0 by substantially more work, but it's not too bad. And therefore, the whole derivative limit, oh, this is 0 plus, really important. Okay, the whole derivative, both sides, exists and is equal to 0. Okay, so that's good. So that means we're starting to fill in what the graph of the first derivative would be. It's clearly 0 here. It wasn't clear until we did this careful calculation what it was at the origin, but it's equal to 0 there. And then it starts going up, and then if you think about the graph I just had, it goes up and then it peaks out and comes back down. That's not super crucial for this stuff, although for the supplement, I am going to go through what these graphs look like of the derivatives a bit more carefully. Okay. All right, so now, yeah, so D, we just summarize that. F prime of x is, okay, so now I need to actually get at least a formula for this to have some control over what happens when I do multiple derivatives. Okay, and that's going to be derivative of e to the something is e to the something times the chain rule. The minus signs cancel. You get 1 over x squared, and then it's 0. The mistake a lot of my first-year calculus students make when they take the derivative of a piecewise function is that they assume that whatever happens at the breakpoint just follows along from whatever happens at the two sides. That's absolutely not true. You can totally have a function that's nice derivatives up and to both sides of the breakpoint, and they might even be equal, but you can't say it's differentiable unless you really carefully analyze it. But we've carefully analyzed this guy. Okay, so that's f prime of x. Now let's go one step further. It's not incredibly exciting to produce a piecewise function that has one derivative. It's the infinite derivatives that's really kind of surprising. Okay, so now we're going to look at f double prime of 0 minus, it's obviously 0, coming from the right. Just write down the definition, and this is where it's really good to have this function. H goes to 0 plus, because we're coming from the right, over h. So it's going to be 1 over h squared e to the minus 1 over h minus, and then of course we need f prime of 0. That's where it's absolutely crucial to know that, but it is just 0. Alrighty, so I'm going to change variables to y again. Y is going to go off to plus infinity. This is going to be an e to the minus y. Together we've got a 1 over h cubed, and so that's going to be a y cubed, because y equals 1 over h. Aha! So now, that's of course y cubed over e to the y. Now do L'Hopital 3 times. This will never change. This goes from y cubed to 3y squared to 6y to 6, and we get that that's going to 0. Okay, so what we see is repeated uses of L'Hopital are going to be crucial, and we're just going to go ahead and summarize that. This is how we really need it. The key fact. And it's just, again, saying that exponentials grow really quickly, and so e to the minus dies really quickly. And that's that the limit as, let's say, y goes to infinity of any polynomial whatsoever times e to the minus y is equal to 0. And again, the proof is you just take it over e to the y, rewrite it, and then use L'Hopital. This will never change, and you just take repeated derivatives over and over and over again until this stops going to infinity. This is still going to infinity, and the limit is 0. Okay, so a nice way to say that, and it's just super good to have this intuition, apart from like formulas and L'Hopitals and stuff like that. Exponentials dominate polynomials, period. And we'll keep coming back to these ideas of which functions tend to be bigger. Orders of growth, things like that, are so incredibly important in analysis. So it's a good example of a qualitative statement that we're really using here. Okay, so we don't want to keep doing this and getting grungier and grungier explicit formulas. It's time to do an induction, but that would be good for the next video. These videos are going to be getting a little long. So we got the idea, though. We now know that f double prime of x is going to be something, an explicit formula we actually aren't going to do too explicitly for x greater than 0, and then 0 for x less than or equal to 0. And then we're going to go to like a kth derivative, or an nth derivative, I guess, in the next video.